In this video, we're going to talk about finding the slopes of these polar graphs, which seems kind of backwards since we already did the area, but it's not, so there. So suppose we want to find the derivative. We've graphed all these polar coordinates in a polar graph, but if we want to find the slope at a point, we still need dy dx. We can't say dr, we can find dr d theta, but it doesn't tell us the slope of the curve in the plane. So let's see how we go about doing that. As you will recall, x is equal to r cosine theta, and y is equal to r sine theta. So to get dy dx, that is the same as saying dy d theta over dx d theta. Let's do this. Keep in mind, r is really r of theta. It's a whole function there. So dx d theta, I have to use the product rule. So I have the derivative of the first times the second, plus the derivative of the second, which is negative sine, plus the first. To find, oops, sorry about that. To find dy d theta, I say derivative of the first, leave the second alone, plus the derivative of the second, leave the first one alone. So dy dx is going to be r prime theta sine theta plus r of theta cosine theta all over r prime of theta. You can't see any of this. I really should pay attention to what I'm doing. Let's try this again. I'm just writing dy d theta over dx d theta. On the bottom, I'll have r prime of theta cosine theta minus, because dx is on the bottom, minus r of theta sine of theta. So what can we do with this? Okay, well, let's try to find some derivatives. That won't be a pain in the, that'll be fun. Let's say r of theta is equal to 1 plus 2 sine of theta. Now, if we were to graph that, we know we would have what we affectionately have been calling a loop-de-loop. Yeah, that sucks. Let's try again. So at 0, I'm at 1. Well, that's a little bit better, but not a whole lot better. I want to find the derivative of this. So I need dy dx rather. Dy dx. I have, okay, so if I do the y function, so I will have, maybe I should go ahead and say what r prime of theta is. So the derivative, I have, or dy dx, I have 2 cosine theta times sine theta. And again, I'm just following the formula here. I'm just following the form here. I have the derivative times sine theta plus the function, which was 1 plus 2 sine theta times cosine theta, all over, let's see, derivative of r times cosine theta minus the function times sine of theta. Isn't that pretty? Should we clean this up a little bit? So multiplying through, I have 2 cosine theta sine theta plus cosine theta plus 2 sine theta cosine theta. Well, that's going to be cool. On the bottom, does it turn out pretty? Probably not. 2 cosine squared theta minus sine theta minus 2 sine squared theta. That can bring TP together. So I have 4 cosine theta sine theta plus cosine theta all over. Okay, so we have the derivative, the slope of this curve at any theta. What can we do with it? What can we do with that, you ask me? Well, I will tell you. The first thing we're going to do is the standard, let's find a tangent at a certain point. So let's find the tangent and normal equations. At pi over 2. So, not pi over 4. Okay, what's pi over 4? Pi over 4, I'm going to get 1 plus the square root of 2. So there, I'm looking for this. And I'm drawing it. I may not be drawing that correctly. So we're just going to move it away so you can't see. First off, what are the points? Well, my x point is r of theta cosine of pi over 4, or r of pi over 4. So I have 1 plus 2 times sine of pi over 4 times cosine of pi over 4, which is 1 over the square root of 2. Multiplying through, I have 1 over the square root of 2 plus 2 times 1 over the square root of 2 times 1 over the square root of 2. Gives me a lot of square root of 2's. 1 over the square root of 2 plus 1. My y value, let's say I already know, or did I multiply through? Damn it, I already multiplied through. So I want 1 plus 2 sine of pi over 4 times sine of pi over 4. I should get the same damn thing. Because sine and cosine are the same thing. Of pi over 4. So I have my points, as ugly as they are. I want the slope, which is dy dx, which will be, should I back to this? Maybe not. I will have 4 times 1 over the square root of 2, 1 over the square root of 2, plus 1 over the square root of 2, all over 2 times 1/2 minus 1 over the square root of 2 minus 2 times 1/2. This is gross. Okay, so this is 2 plus 1 over the square root of 2. These will subtract off, so I have negative 1 over the square root of 2. Flip it through. Now, we have all we need to make a line. I have my x-coordinate, my y-coordinate, and my slope. I have not resorted to decimals yet because I am a pure mathematician. So, tangent line. Equation for a line in general is y minus a y-coordinate equals the slope times x minus the x-coordinate. For the tangent line, I have y minus my y-coordinate, which is 1 over the square root of 2 plus 1, is equal to the slope, where the slope go here, 2 times the square root of 2, negative 1, times x minus the same x value. And that's the pure form. I'm not multiplying it out, although I will give you the answer in decimals. Y equals negative 3.83x plus 8.24. Now, to find the normal line, the only difference is your slope. The slope is the negative reciprocal. So I have y minus 1 over the square root of 2 plus 1 equals 1 over negative 2 square root of 2 minus 1 times x minus 1 over the square root of 2 plus 1. So this isn't hard, it's just you're going to get a writer's. If I switch this into decimals, I will get y equals 1 over 3.83x plus 1.26. That's the normal line. Okay. Another thing we might want to know is, where is our tangent horizontal? A line is horizontal when the derivative is equal to 0. dy dx is equal to 0. And what was my dy next again? That hideous thing. And so we have 4 cosine theta sine theta plus cosine theta all over 2, bring this together, 2 cosine squared theta plus sine, nope, different signs, minus sine squared theta. Oh, that doesn't look much better. Minus sine theta. A fraction equals 0 when the top equals 0. So that means I have, so I can go ahead and suck out a cosine here. Cosine of theta times 4 sine theta plus 1 equals 0. That equals 0. And cosine theta equals 0, or 4 sine theta plus 1 equals 0. Cosine equals 0, there. When theta equals pi over 2 and 3 pi over 2. And this one's not as pretty. Let's see. Sine of theta equals negative 1/4 theta arc sine of negative 1/4. I don't know this one. Oh, I'm going to go grab Maple. That's Maple's way of saying, yeah, I don't want to do this. I say, yes, you must do this. Tell me the answer, you bet. Okay, so it is, happens at when we have negative 0.2526802551, probably some more radians. Now, arcsine only gives us one answer. Is there only one answer? Sine. So where should we be getting horizontals? So we got the one at pi over 2, and this was the one at 3 pi over 2. Oops, so assume that's a straight line. We have one at negative 0.25 radians, which is the same thing as going all the way around. So that looks like this one, and we should have another one over here. So where would that be? Sine is also negative in the 4th quadrant. So we're also going to get it at pi plus those radians. I tend to look at this between 0 and 2 pi to put this into that chunk. So I'm going to say 2 times pi. So that's where we have a horizontal tangent. I should be able to figure out where a vertical one is. I may not. For a vertical tangent, we would have to figure out, let's see, that would be a vertical tangent, and that would be a vertical tangent. And that's going to happen when the bottom equals 0. That bottom equals 0 doesn't look pretty. Yeah, it's not a good sine one. Why are we getting 4 of them? That's interesting. Oh, duh, I'm stupid. You got them on the inside too. So they're 4 points. They may not be the easiest to find because I'm looking at this cosine squared and sine squared, that's pennies. But that's how you would find it. I think that's a pretty good place to start. We figured out how to find the derivative. We figured out how to find lines of tangency and normalcy. And we know how to find when the determinant, sorry, wrong class. We found when the derivative is 0, or when it's undefined, we might go to Maple and cry, or I'll find something that's easier for you to crank out rather than what we just did. Have a great day.